Okay, welcome back. I hope you had a good lunch. So, and maybe you're all very, very sleepy. So I'll try to keep you all up awake. So to do that, let me do a little bit of recap of what we have done so far. And I will then give you a small exercise, okay, so that you can try to build a model that sort of roughly corresponds to conditions that I will, present. And then so today, in fact, if you look at the schedule, it says game theory session, but I think we will be able to get there only towards the second half of this this lecture. But I will cover that more extensively tomorrow and day after. Okay. So let us start with a quick recap. So we are interested in sort of deriving mathematical models of populations, how they grow, how they change over time. And we have learned to do that in two types of settings. One is discrete time. And the general strategy for modeling is that, you write the population as the next generation as the current population with some multiplied by a factor r. So r determines how populations grow over time, sort of really determines the underlying processes. Okay, so depending on the assumptions you make, this r can take a variety of functional forms. Okay, so you make biological assumptions about the processes. From that you make reasonable guess for what this r should be. Okay, and for example, in the context of competition under limited resources, we said must be a declining function. We said in the context of unlimited resources, this will be a constant value, and so on. So all of them, all of these different biological scenarios will yield you different functional forms of r, and then from that you plug that back into this equation and you have a model of population. Okay, so let us write down this r times xt as f of xt. So once we have developed the model, so what do? We try to analyze the model and try to find the equilibrium solutions. So these are populations at which systems don't change anymore. Okay, and you find that by setting xt plus 1 is equal to xt, which is same as solving this equation. So you find all possible values of x star that satisfy this equation, and then you check which of those equilibrium solutions are stable. To do that, you look at the derivative of f at each of those equilibrium and determine conditions in which this quantity is less than 1. That tells you whether the conditions under which each of those equilibrium will be stable. Okay, that's and then of course, when you run out of all the analysis from these two, you do computer simulations. Okay, so now we have also learned continuous time version of models, instead of writing down the next population size directly, what we do is we actually write a rate of change of populations over time. And here too, we can decompose the growth function into in this format. Okay, so here again r captures the individual level growths and how does that depend on x and other parameters. Again, depending on the biological context, we basically think how this r must depend on x. Okay, under simple conditions like unlimited resources, we have a constant r. Under a scenario of competition for resources, you can have linearly declining or more complex functions. And each of those different functional forms of R will give you different models. And then now let's say we have this general equation. Again, you can define something called an equilibrium. Here the equilibrium corresponds to the fact that the populations don't change over time, which means dx by dt is equal to 0, which you find by setting f of x to 0. And secondly, how do you find stability? You again look at the derivative of this function with respect to x, evaluate them at the equilibrium. Whenever this condition is satisfied, you concluded that the equilibrium is stable. Otherwise, if it is greater than 0, it's an unstable equilibrium. Okay. So that's how we write the model and analyze the model. Okay. Now there is a very simple and nice graphical way of understanding both equilibrium and stability for both the cases, and that works really well for the continuous time scenario, and I will demonstrate that with the example of the logistic model. Okay. So of equilibrium and stability. Okay. So let's consider the logistic model. Okay. So one thing that if you thought about issues of carrying capacity and so on and so forth yesterday, you must convince yourself that in this continuous time version, K is indeed carrying capacity. Okay. So I will leave that as an exercise for you to think and convince yourself that's a good interpretation. Okay. So that's not the focus of what we are going to do today. So the idea of graphical analysis is, can we implement these two conditions without actually solving any equations per se? Okay. Can we intuitively understand equilibrium and stability from graphs? So the idea is that the equilibrium solutions are given by f of x equal to 0. So what does that mean? If I plot the function f as a function of x, all the point it touches the y is equal to 0 axis, or the x axis basically, will be equilibrium solution. Is that right? So if I plot f as a function of x, all the points that this f will touch cross this x axis correspond to f of x equal to 0. Therefore, they must all be equilibrium solutions. Right? Therefore, the moment I write down the model, all that we have to do is plot the function f using any plotting mechanism. There are many ways to plot using computers these days. So can we do that for this simple logistic model? How will this function look like? I'd asked you to plot in one of the exercises yesterday morning. I don't know how many of you did. How does this function look like? Assume R0 is positive. So you have x into 1 minus x over k. Okay. So how do you plot any function? First, look at when they are 0. And in fact, it's fairly clear in this case that it's a quadratic function. And for those who are familiar with the quadratic function and a parabola, this actually is, it looks like this. Right? It is 0 when x is 0. When x is between 0 and k, this is positive, so therefore both are positive. When x is very, very large, this term becomes negative, therefore it's a negative value. When x is negative, of course, this becomes negative, therefore this is negative again. And it's a symmetric function of this type. Okay. So this is, of course, a very simple quadratic equation, so it's easy to plot. If there was a more complex function, you can use Mathematica, MATLAB, or any of these programming languages to plot the function. Of course, you have to assign specific values when you don't know the complex form of the function. So once you have plotted that, what do? You identify all the points where system crosses the x-axis. The plot crosses x-axis. In this case, obviously, it is 0 and k. And those two correspond to equilibrium solutions. So what the next thing to do is, circle all of these equilibrium. That way you know where they are. And for a more complex model, you can have this can come back and it can go back, it can have more complex forms. It can also be asymmetric, it could be like this. So there is no reason that this will be the form of the function for other cases. So once you have done, now how do you identify? So we have done this part now. Now how do I do the stability? Okay, so I don't actually have to calculate this at all. It's much easier than that. So let's try to understand what is f. F is dx by dt, right? It tells me how does population grow. If f is positive, what will happen to x? F is positive, dx by dt is positive, population has to necessarily increase. Okay, so remember these two simple rules. If f is greater than 0 at some value of x, this implies x will increase further. Is that right? Because dx by dt is equal to some positive value means that the growth rate is positive, therefore the population will increase. Conversely, if f is less than 0 at some x, implies x will reduce further. In fact, I can even say reduce, increase with time. Okay, so we will just apply these two rules. So how do we find stability of any equilibrium? We go to the equilibrium, make a perturbation, and then check whether the population will now grow or reduce, right? Can we just do it now? Let's say we are at 0. Let's say we made a perturbation to this value, some small value of population size. What is the growth rate of population here? It's some value which is positive, therefore x will increase further. So any change that I have made will increase further. Let's say it now becomes this. What will happen now? It's again positive. It will again increase. So it will basically keep on increasing. For any starting value of population in this region, it will keep on increasing. Are all of you convinced with this? To arrive at this conclusion, we did not have to do any integration, right? All that we had to do was plot f as a function of x, and then for any location, look at what was the sign of f. If f was positive, x has to increase. If f is negative, it has to reduce. Now, this already shows you that 0 is an unstable equilibrium. This simple graphical analysis already demonstrates you, without calculating these derivatives, that it's a stable equilibrium. Are all of you convinced with this? Is it a very simple, reasonable argument? Now let us look at what happens at another equilibrium, which is x equal to k. Say x equal to k is here. So now if I make a perturbation, there are two ways I can make a perturbation. One is that I can make a perturbation to the left or to the right. This corresponds to removing a few individuals from the population. Okay. Whereas this corresponds to adding a few individuals. If I remove a few individuals, what happens to the growth rate? It was 0 in the beginning. By removing, the growth rate is now positive. Therefore, the system will push you back towards this k. On the other hand, if I increase the population size, the growth rate is now negative, which means x will now reduce with time. Therefore, and in fact, even if I had made a much larger perturbation, it would still be the case that the growth rate is negative, therefore system will push back towards k. So what you can clearly see from this sort of a flow diagram is that near k, population, any perturbation will flow back to k. So we usually denote stable equilibrium by solid circles and unstable equilibrium by open circles. Any questions on this method? And you can apply this to any complex function. Okay, let's hypothetically imagine that, let me finish let me let you take notes that you are taking. Let's say if you had a much more complex form of f, hypothetically, I won't tell you why this might happen. Let's say if f looked like, you know, how do we do? What's the first thing to do? Find all the equilibrium solutions, which are going to be these. Is that right? So, and is this stable or unstable? The first one. To do that, all that I have to do is do a perturbation. So if I made a left perturbation, meaning I have reduced the population density, but f is positive, meaning it will increase the population size. Therefore, it will be this. On the other hand, if I increase the population size, the growth rate is negative. Therefore, any increase will be diminished. Yeah. Yeah. I never said where x is 0. X is 0 only here. F is 0 at all these intersection points. Okay. So is that clear now? Because of that, this is a stable equilibrium. What about this? The next one. Is it stable or unstable? Unstable. Why? Because any decrease I do will have a negative growth rate, meaning population will reduce further. Any increase I do will have a positive growth rate, therefore it will again go away. So in both directions, system is going away from the equilibrium. So what about this now? The next one. This is now therefore unstable. How about the next one? Stable. This one? Stable. Unstable. Unstable. Imagine if it were to cut once more, what would that be? Stable. So in fact, you can also see a pattern here. A stable and unstable equilibrium always alternate. You can't have two consecutive stable equilibrium at all. Okay. So this is how we can easily analyze, at least diagrammatically understand various equilibrium points and whether they are stable or not. Okay. Yeah, you have a question. This one? Yeah. Yeah, that's right. Yeah. His question was, if you integrate this equation and if you plot x as a function of time, will that be a sigmoid? It will look like a sigmoid. It will initially have a rapid exponential growth and then saturates to a k. That's right. Okay. Any other questions? No. So now that you have learned, let's do a simple exercise where I hope to give you a simple scenario, and I want you to construct a model for the scenario. Okay. So far we have been talking only about computation, right? Okay. Which is of course highly prevalent in all natural biological populations. But we also know that organisms, in many instances cooperate with one another. What is the meaning of cooperation? Competition, what is competition? What does competition do to individuals? It will negatively affect their fitness, right? So in the simple context that we have been thinking, we can think of R as some measure of fitness for individuals. So increasing populations will reduce fitness. What does cooperation do in contrast? Positively affect the fitness. Okay, is that fair enough? And that does happen, right? So let us think of a scenario where there is of course this is probably a hypothetical scenario. There is some bacterial population. Okay, and you have heard of probably something called quorum sensing. Is that right? Okay, what is quorum sensing? What happens in quorum sensing? Somebody take a mic and please speak up. Nobody wants to? Yeah, go ahead, please.
So when there is a particular number of cells reached or density of a population which is reached, so bacteria, they have certain signals which is transmitted, and it can be seen in the production of a particular protein or let's say fluorescence. So things like that happen only when only once when a particular density is reached, and they together as a unit pass on the signals.
Exhibit some new behaviors when they reach. Now, does that, are there instances when that also can help everybody in the population? Okay. So what's the consequence of the individual fitness? Better now, right? Okay. So now, yeah, go ahead, yes. How does competition reduce one's fitness? Yeah, we're talking about relative fitness. Well, in equilibrium, everybody has equal fitness. Everybody in the population will have equal fitness in equilibrium, right? Okay. But so imagine that for a given population in this generation, if I increase the crowding, what will happen to everybody's fitness? Individual fitness should remain the same. For the same amount of resources, if I increase the crowding, say that again, sorry? What do you mean by fitter? Relatively fitter individual will be fitter, but will that relative fitness be higher than the case when there was less amount of crowding? Yeah. I mean, it's relatively fitter individuals remain fitter. I'm not disputing that at all. But even for those guys, if you were to compare the fitness under less crowded versus more crowded conditions, what will be the case? More crowding will reduce that, even the fittest guy's fitness, right? Is now under a harsher condition. Yeah. And of course, in all ecological models, we assume that everybody has the same phenotype. So there's no question of selection here to some extent. Okay. Yeah. So anyway, so let's think of a hypothetical. So you all know something about quorum sensing, and there are some positive effects that actually kick in when individuals are at some minimum amount of densities and above. So I'm going to give you some conditions here. Imagine there is a bacterial population which at low densities, they don't survive well, So I'm of course intentionally being vague when I'm using these words, and that's also intentional. And I want you to therefore convert them to a model. If I give you extremely precise statements, I was as good as saying the model itself, right? So I'm obviously going to be slightly vague here. Don't survive well. Okay. Above some density, let's call that xc, xq, they exhibit quorum sensing. And everyone has higher fitness. Okay, is that fine? And further, when population sizes are really large, when densities, let's talk about densities throughout. Competition over X. Is that fine? So now I want you to incorporate these three information into a model that tells me how does density of bacterial population change over time. Is the question clear? So until now, just to be very clear, we are on the same page. We have been working in this limit only. Now we have been trying to model this only, but I'm telling you that something interesting happens at lower densities. Can you write a model now that accounts for all the information put together. So I'm going to give you, I have 43 more minutes. So I'm going to give you maybe 10 minutes to think about this question, and then we will come up with a model and discuss that, and then apply the same type of techniques, and then solve the population equilibrium and stability and so on. Okay. So take your time, think about this, and come up with a new model. So I don't, by the way, just to be very clear, I don't really care whether you can write down an actual mathematical expression here. What I want is a graph that depicts this growth pattern. Okay. So do you understand what did I mean by that? Okay. Yeah. What do you think it should be? What do you think is the graph that would be ideal to do? Huh? That's a good question. Huh? Huh? Okay. So somebody said population something R and X. What did you say? Yeah. You said 1 second. That would be the entire model, of course. But go visit this part of the board. How do you go about building model? So general framework is this: you incorporate process in this and then substitute back. So basically what, I forgot your name, Harsha said. So you have to basically convert whatever I have said in words to a graph of this type. Okay. So basically if you show me a graph of this type that incorporates these things, I'll be very, very happy. Working? So see, R is birth rate minus death rate. It can be negative or positive. But you think of R, as equivalent to fitness. It is similar to fitness, not quite numerically fitness. Because fitness by definition cannot be negative, right? It's a number of offspring. It can only be 0. It can't be really negative at all. So what I'm really looking for is R, not exactly fitness. So therefore remember that R can be negative. And also I want to give you one more point, one more point, that if R is never negative, what will happen to populations? The births are always greater than deaths. That means they will just keep on growing forever. So any model of any type, if they have to stop at a finite population size, R must necessarily be negative somewhere. Okay. Excellent. So I'm really pleased that almost everyone that I have gone to are actually able to develop the model that incorporates these points. Of course, because I have been slightly vague in the way I have written, there are some variations in the way you have done, and I had also allowed possible some small misinterpretation, which has also happened, but that is again a consequence of the way I have written and nothing to do with the fact that you probably misunderstood it. So let us try to translate this into a graph. So as we discussed even before you started, we are looking at R of X, which is basically per capita growth rate, which measures the probability of an individual, surviving and reproducing. And how is that changing with X? So at low densities, I said they don't survive well, and there are two interpretations that all of you have come up with for this statement. They don't survive well can be interpreted to mean their birth rates are small, but still better than death rates. That's one possible interpretation. So many of you have written a very sort of a low slope, but positive growth rate for low densities, followed by the fact that the quorum sense kicks in, and therefore there is a higher growth rate phase, followed by a scenario when the computation kicks in and that changes the direction of the per capita growth rate. Okay, and eventually when competition really overtakes, again the deaths will dominate births. This is something that some of you have missed. So eventually this does become negative. And as I mentioned, if this graph never really reaches negative, it's always positive, the population will just keep on growing forever. And that doesn't make sense under the sense that every population is eventually limited by competition for resources. Okay, so they have to cross the zero axis and become negative for some value. Okay, so let's call this k. Okay, so here was the part that was a bit ambiguous. So what I really meant when I said that they don't survive well was that at low densities the death rates are actually more than birth rates. So by which I meant that initially the per capita growth rate is negative. Beyond a density xq it becomes positive because of quorum sensing related phenomenon, and then quorum sensing dominates before the competition kicks in. Okay, and in fact many of you actually did get this right, even with one small discussion with me clarifying what I meant in the first sentence. Yes, do you have a question? Yes, it will. That means that if you start with a population that is less than xq, in this scenario, the way I have described, they will collapse. Yes, that's actually right, absolutely right. Under these assumptions, which are of course simplistic and so on. Okay. Or maybe one can say that, of course, this is overly simplistic. Of course, maybe they will survive in a very low densities, but not, which can be effectively seen as zero density as well. Okay. Okay, so this is R versus X. Now how do we analyze? So are all of you happy with this description of the graphical description of the model? So now how will F look like given this R? F is nothing but R times so multiply this function with X. Is that right? Okay, so how does this look like? So in this region between 0 and xq, you have a negative number for the R, and you're multiplying with by an increasing function, but always positive. So does the sign change here? Sign doesn't change. So the f will also remain negative. But what will be x when x is close to 0? Because x is 0, this will become 0. But what happens at xq? It again remains 0 because this becomes 0. So it is 0 here, 0 at xq, and remains negative in between. Okay. And then between xq and k, both the functions are positive. So some changes will happen in the intermediate regions, but the overall shape will still be like this. And again, for greater than k, R is negative. This is some large number, but overall it will still be negative. Okay, so this is the individual per capita. This is the per capita growth rates. This is the population growth rate. Is that fine? And this is the complete model of the population dynamics now. So I just gave one example of quorum sensing here. What are the other instances that you can think of, other reasons, other biological reasons that you can think of? When they are in low densities, they have a high death rate, but they will do well only beyond a density. Can you think of other biological scenarios when that might be true? Say it again. Use social animals, and what did you say? Biofilm, okay, yeah. I mean something similar, something similar also happens there. Cooperative behavior, that to kick in you need a minimum density, yes, that's right. Other scenarios, higher organisms, yeah? Why? Why do you need a high density for survival there? Okay, so you're saying that the effects are prominent only when they're above a group size, otherwise it's actually not much. Okay, anything else? Another reason that this can also happen is when they're in low densities, it might be hard to find mates. Okay, it might be hard to form groups. That also provides many other benefits. So therefore, they have an effective low population growth rates, in fact negative population growth rates, and they survive only above a density. Okay, okay, and in fact that's also called. So okay, now before we go there, also now that we have built the model. We have thought about many biological scenarios that can cause this. How do we identify equilibrium now? What are the equilibrium solutions? Wherever f crosses x, not r. Again, don't mistake that. It's not r crossing x, it's the f, a function f, the entire population growth crossing the x-axis. What are those? 0, xq, and k. Which of them is stable? Is 0 stable? Let's say if I add a few individuals, what happens? The growth rate is negative, so it comes back. And that's true in the entire region. So therefore 0 is an unstable equilibrium. Okay. What happens to xq? Oh, is it stable equilibrium? Is it stable? Come on, please correct people. I know. I'm checking if you're awake. There is stable equilibrium. Does perturbation to negative values make sense? It's not biologically meaningful, so let's not bother with that. What about xq? If I make a perturbation to the left, what happens? It's a negative growth rate, so it will reduce even further. On the other hand, if the system was at x and if I add a few individuals, what happens? The growth rate is positive, so population will increase. I will keep on increasing up to this k. Is that fine? And then if you are at k, if I add few individuals, the negative growth rate, it reduces again. If I subtract, it increases, it's back to k. So k is a stable equilibrium. So start at xq. Let's say if I add a few individuals, what is the growth rate now? It's given by f, right? And f is positive. So read that rule. If f is positive, x will increase, right? So it will now increase. On the other hand, if I make a negative perturbation, reduce a few individuals, it's negative, the x will reduce. So either way, it's going to go away from x. Is that fine? Okay. So, which means that if you want the population to reach the carrying capacity k, you need to make sure that they never go below a threshold density. If they ever go below a threshold density for any reasons, they might just collapse to extinction. There might be local extinctions in those areas. On the other hand, if you want to introduce a new species, this species into a new area for rehabilitation, if you introduce them in a very small number, again they will collapse. You have to ensure that you introduce in a certain minimum number for them to grow to their carrying capacity. Okay, and this is also called Allee effect in ecology. Yeah. So imagine that there is a population that exhibits this kind of dynamics, meaning they have negative growth rates below a threshold value of population, but positive only above it. In this population, you always want to make sure they never go below this xq value. Otherwise, let's say if you have to shrink their, humans always disturb habitats, right? If you shrink their habitats to an extent that their numbers are less than xq, they will immediately collapse to an extinction. That means they need to have a minimum size for them to sustain. On the other hand, if you imagine another scenario which again is not an unusual scenario, where we know that a population has gone extinct from an area, but we want to reintroduce the species in that area. Okay, if you are doing that, you want to make sure that you start with at least a minimum number. In the absence of that, they will just collapse to again extinction there. And this principle of Allee effect is extremely important in conservation of many species, which is why you might hear news like you need to have a minimum habitat size for these type of animals to survive. Okay. Any further questions? Yes.
So I was just wondering about this Allee effect. It's a deterministic systems, right?
Yes.
But people also talk about evolutionary rescue in finite populations. There also you need a minimum number so that, do you know how they're connected?
Correspondence between the two?
Sorry?
The correspondence between the
Yeah,
two?
or correspondence, or are they, which is more realistic, or?
I think both are really important though. So in fact, what will happen is that
Here
if
you
there are
have finite
systems
fraction.
with Allee effect in the deterministic limit,
Yeah.
and if they also have finite population size, this XQ can actually increase even more. Because the demographic noise can also cause collapses, right? Right? So there will be additional reasons for a system to collapse now. That will, I think, enhance the XQ required for a stable population. In fact, there is one of my students' paper where we show that even though there is no threshold value required for a deterministic limit, when you have finite population size, you actually end up having to maintain a minimum population.
Just out of curiosity, let's say if this graph was like
Can you speak up a bit? No, please use the mic.
Just out of curiosity, let's say if the graph was like a parabola, let's say on one side, if we make perturbation, it will come back to equilibrium, but on the other side, if we make the perturbation, it will just move away from it. What
Is
kind?
Biologically reasonable?
Yeah.
Is it?
That's what I wanted to ask. And what kind of equilibrium will it be known as? Is it partially stable equilibrium or?
I don't understand. Imagine you are saying this never happened, is it?
So if it was like U. Okay.
Like say like this.
It's not going below. It's just touching the.
Oh, like always like this.
It's just touching the x-axis.
Right. Okay.
Then so if on one side if we bring perturbation, it will come back to that one. But if we bring the perturbation on the other side,
yeah,
it will just move away from the.
Yeah. So I think there is a name for those kind of. What is it? No, that's not this is bistable. There's some name for that also, but I think those are very peculiar situations that probably don't happen in. I don't know. Okay. I mean, he was just hypothetically imagining a scenario where f as a function of x looks like this. Oh, sorry, this is just touching. So if you move here, it will actually go this side. If you move here, it will go. So is that what you're saying?
If you move it to this side,
it
will come back here because the cap is positive.
Right. Yeah, it will come back. Yeah. And again, if you this I mean, this is a very peculiar case. I wouldn't imagine why this must be such a special case must happen in a biological system. Okay, so all of you now have some handle of building models, analyzing them. Okay, and these type of analysis are also, I think, very helpful in many PopGen models, right, Kavita? Okay. This is, I think, I don't know. There's some name. I don't know the name. Yeah, I mean, it's not globally stable for sure. I mean, some perturbations are stable, but not every perturbation, right? So, I mean, so in a two-dimensional space, you call them saddle points. I don't know what is it called here. Partially stable. I don't know. Some name. I don't know. Yeah, Dilip. Partially stable. Okay. Any other questions? Okay. So now, how much time do I have? 15 minutes. Now we have done a lot of population dynamics. Now, how do we make connections to evolutionary dynamics? That's where I am now slowly going to come. And I will make that connection today, and then I will sort of elaborate more on that. So now we have been thinking of a single population, computation within that population, right? And that gave rise to these type of very, very simple models. But the tools of analysis I want to emphasize will be true. If your population genetic model looked like dx by dt is equal to f of x, everything that we have done can be applied to the same model. You just have to reinterpret what is that x now. Okay, and often the simplest population genetic models, you consider two alleles, allele A, allele B, or you can call them allele 1 and 2, and so on. And you're often interested in not the absolute numbers of either of them, you're interested in the frequency of occurrences of alleles, right? You know this really, really well, I don't have to tell you. Let's say that P is the frequency of allele A, and Q, which will be nothing but 1 minus P, the frequency of allele B. Okay. Let us say that omega A represents fitness of allele A and omega B is fitness of allele B. Okay. This entire population, let's also define an average fitness. Let's call this omega bar. What will be the average fitness? It will be given by frequency of AP with the corresponding fitness of allele A with frequency of. Is that fair enough? Is all of you agree with this? This is the average fitness of the entire population. Okay. Given this, now if you were to basically keep track of every individual in the population and how they are changing given this fitness for A and B, because now there are basically lots of allele A's, allele B's, they will both have, each of them will have omega A babies, the A's will have omega A babies, B's will have omega B babies, right? So each of their population has changed now. So I can write down a similar sort of, population has changed from, let's say, NA was the population size for, let's say, A, and NB for this. If I now do a delta NA, and if I keep track of all of the simple algebra carefully, and what is that we're often interested in, we want to change the, look at the rate of change of populations, right? So here the corresponding thing will be rate of change of frequencies. So if you now write down an equation for rate of change of frequencies, okay, let's say allele A, can you guess what the equation will look like? It will be P 1 minus P. So I'll just is it right? That's correct, right, Kavita? According to your notations as this? Okay. I haven't forgotten everything. Okay. So now you see the sort of, although even if you are never interested in understanding population dynamics, all the techniques you learned can be basically applied to this now. So this will be your new f of p, right? This will be the corresponding f of p. So how many of you have seen an equation of this type, by the way, somewhere in, you haven't seen? Some of you have seen, but if you had not seen, nothing that you have lost so far, yeah, go ahead, Kavita. So I say it again? Oh, in this equation, is it? Really? Okay. It's just the average. To the continuous one, it doesn't have. Okay, fine. So yeah, that's fine. Actually, maybe what I did mean in that case, why does it actually go away? I'm a bit surprised. Why does it go away? Oh, yeah, we can discuss this later. Yeah. So the denominator doesn't have omega bar under the continuum time approximations. Okay, but nevertheless, this is how the equation looks like. Isn't it remarkably simple and similar to logistic model that we have studied so far? Okay. Now, how do you go about analyzing this equation now? How analyzing the equilibrium solutions? What will you do? You will plot this entire function, okay, and then look at all the equilibrium solutions, okay. And I think Kavita will do probably many cases of this. Let me do just 1 or 2 cases that will help me in my next class tomorrow. Okay, let's consider simple cases. Case 1. Okay. The thing is, can I plot this? Can I plot this, by the way? I can plot this. We know what is P into 1 minus P, but maybe does this depend on P? Huh? No? How many of you say no? Affirmatively no? Okay, that's great, fantastic. Let us assume it doesn't depend on P. Okay, okay, and in fact, if they don't depend on P, there are some constants. One of them has to be greater than the other, right? Okay, let's assume that omega A greater than omega B. Okay, so therefore this is now a positive. Let's call this R again. Then R therefore becomes positive. Is that fine? So now, if you plot F as a function of P, what do we get? We have P into 1 minus P. This crosses at 1 and 0. Because R is greater, positive, we have an parabola that bends down. And what are the equilibrium values? 0 and 1. 0 corresponding to all B's, 1 corresponding to everybody being in A. And then, which is a stable equilibrium? 0 or 1? 1, confident? Okay, so this is exactly the logistic model, right? Except that K is now is equal to 1. Okay, and in fact 1 is stable, and you can check that by making a perturbation to 0, and we'll find that it decreases because the growth rate is positive. But this will be, of course, more than 1 doesn't even have a meaning in this case. Frequencies can only be between 0 and 1, right? So 1 is stable, which means, does it make sense? Of course, fitness of A was greater than fitness of B. What else did you expect in life, right? Therefore, A should be selected, and therefore everybody will be now A. Okay, yeah. Which terms? Why is this? Oh, okay. Well, I mean, just a simple algebraic derivation. I don't know. How does it come from? Okay. Yeah, you not derive it. I agree. Of course, my intention was not to derive anyway. She will do it. Yes, excellent, great. Okay. So this is very simple. Of course, I could have taken the other way around, in which case 0 would have been the stable equilibrium. Maybe since if omega B was greater than omega A, the entire population will be A. Okay. But what I will discuss tomorrow basically will be the cases when this assumption is not right. Okay, and that's when solving this equation, which will become much more complex, actually interestingly turns out to be exactly identical to using the ideas from game theory and applying it to evolutionary scenarios. Okay, that's what I will try to do tomorrow. You heard of game theory somewhere in life? So yeah, so that's what I will show you tomorrow. Okay. So tea break. I mean, unless you have more questions. Any questions? Great. Until now. Thanks.